Hello students, in the previous lecture we discussed about the enemas, aerobes, and in the last we discussed about the problems in the formulation of monophasic liquids. Uh, so today we will discuss in detail the problems uh, which are which comes while the formulation of liquid dosage forms. So first of all we will discuss about the solubility. So the extent to which the solute dissolves at a particular temperature, it is known as its solubility at that temperature. So usually 20 degrees centigrade is considered to be the optimum temperature for the preparation of the stable saturated solution, because it is considered as room temperature at which the drugs are supposed to be kept. So when the substance dissolves in a given system, there must be interactions between solvent and solute molecules or ions, and dissolution of solute in solvent results. So during this phenomena, through thermodynamic functions such as free energy, enthalpy, and entropy change, and that is why when a solute is dissolved in a solvent, the dissolution is generally accompanied by absorption or evolution of energy in the form of heat. So So non-energy changes are involved in the dissolution process if the forces of attraction between the solute-solute molecules and the solvent-solvent molecules are exactly equal. So to visualize this molecular interaction, one has to study the effect of various physico-chemical parameters on solubility behavior. So this helps in predicting type of interaction and extent of solubility. So melting points can easily be correlated with the solubilities of some compounds, that is MPS, and solubilities of some barbiturates, which are given below, indicating decrease in solubilities of compounds as the melting point increases. So let's discuss. We have the table 5.1, which is a correlation between the melting points and solubilities of some barbiturates. First of all, there is a compound. Second will be melting point of that compound in centigrade, and third one is value of water required to dissolve 1 gram. So secobarbital, whose melting point is 95 to 96, volume required of water to dissolve 1 gram secobarbital is 2 ml. So in the same, pentobarbital having melting point 132 to 133 degrees centigrade and volume required is 3 ml, and amylobarbital having melting point 155 to 156, having water required 5 ml. Phenobarbital having melting point 174 175, having value of water or volume of water required 10 ml, and barbital having melting point 188 to 189, having 14 ml. So polarity of the solvents is another important criteria in predicting the solubilities of the solutes, that is its dipole moment. So depending on the dielectric constant of the solvents, they are classified into three classes: polar solvents, non-polar solvents, and semi-polar solvents. So polarity of some solvents and solutes are given in table 5.2. So polarity, decreasing polarity, so solubility, so decreasing water solubility. So this table also dielectric constant of solvent, that is approximate value, and solvent and solute. So students, the dielectric constant is the solvent's property, which is an energy required to separate two oppositely charged ions in a solvent as compared with energy required to separate the same oppositely charged ion in vacuum. So water has high dielectric constant equal to 80 at 25 degrees centigrade, which reduces the force of attraction between oppositely charged ions in crystal like sodium chloride. And chloroform has a dielectric constant of 5 and benzene about 2. Hence, ionic compounds are practically insoluble in these solvents. So, polar solvents break covalent bonds of potentially strong electrolytes by acid base reactions. And since these solvents are amphiprotic in nature, so for example, water brings about the ionization of HCl as follow. Then HCl combined with the water gives hydronium ion and chloride ion. So the weak organic acids, alcohols, aldehydes and ketones, they are not ionized appreciably by water. Their solubility is attributed instead to the hydrogen bond formation in water. So the polar solvents are capable of solvating molecules and ions through dipole interaction forces and particularly hydrogen bond formation, which leads to the solubility of the compound. So the solute must be polar in nature to find a place in the associated structure of the solvent. So the ion dipole interactions between the sodium salt of oleic acid and water may be shown. So students, uh, always in the non-polar solvents, they are unable to reduce the attraction between the ions of strong and weak electrolytes because of the solvent's low dielectric constant. And also they do not break any covalent bonds and ionize weak electrolytes since they are aprotic in nature, so they cannot form hydrogen bridges with non-electrolytes. Hence ionic and polar solutes are not soluble or are only slightly soluble in non-polar solvents. So however, non-polar solvent resolve non-polar solutes with similar internal pressure through induced dipole interactions. So the solute molecules are kept in solution by the weak van der Waal London type of forces. Thus, oils and fat dissolve in carbon tetrachloride, benzene, and mineral oil. So, semipolar solvents induce a certain degree of polarity in non-polar solvent molecules. Example is benzene, which is readily polarizable, becomes soluble in alcohol, acetone, and increases the solubility of ether in water. So, Hildebrand has shown that the consideration of dipole moment alone is not adequate to explain the solubility of polar substances in water. So, the ability of the solute to form hydrogen bonds is far more influential factor than is the polarity as reflected in a high dipole moment. For example, dipole moment of nitrobenzene is 4.2 into 10 raised to power minus 18 ESU per centimeter, which is far more than the phenols. So, but nitrobenzene is soluble only to the extent of 0.0155 mole per kg in water, while phenol is soluble to the extent of 0.95 moles per kg at 20 degrees centigrade. So then we have table 5.3 on page 154, which shows and which table shows solubility parameter of various compounds. So, so students, more similarity in the structure of solute. Solubility enhances the solubility of solute in that solvent. So polar solute dissolve in polar solvents while non-polar solute dissolve in non-polar solvents. And also the addition of groups like OH, CHO, CHOH, CH2OH, COOH, NH2, etc. They tend to increase the solubility of organic compounds in water. So addition of non-polar groups tend to decrease the solubility of compounds in water. So introduction of halogen group tend to decrease the solubility, while branching of chains increase the solubility in water. So solid compounds of high molecular weights they are generally more difficult to dissolve in water. So there are few techniques available in the solution technology to enhance the solubility of poorly soluble compounds. So pharmacists must adopt them in the formulation of liquid dosage forms if desired concentration of poorly soluble drugs have not been achieved by simple dissolution techniques. So these techniques are solubilization, co-solvency, pH modification, complexation, hydrotropy, and chemical modification. First one is solubilization. So this technique was introduced by McBain in 1937. So it is the dissolution of purely or poorly soluble solute molecules in water in presence of surfactants and forms thermodynamically stable solution. So the process of dissolution in presence of surfactants, it has been described as the formation of micelles, which enhances the solubility of poorly soluble solute. When surfactant of proper HLB is added in low concentration to liquid, it tends to orient at air-liquid interface. So if surfactant is continued to be added in higher concentration, air-liquid interface is fully occupied, and at still higher concentrations, the surfactant molecules or ions, they are forced to go into the bulk of the liquid. So when the particular concentration of surfactant molecule is maintained in the system and aggregates of surfactants are formed called micelles. So the concentration of surfactant at which micelles formation takes place is called critical micelle concentration. So that is most important point. So micelles may be of various shapes like spherical, sausage, road and lamellar, and micelle formation increases the solubility of solute by virtue of its dissolving in or being absorbed onto the micelle. So the function of surfactant starts only at CMC and increases with the concentration of the micelles. So solubility enhancement of cresol solution with soap solution is a very good example of this technique. So as such, cresol has only 2% volume by volume solubility in water, but with soap solution, we can dissolve up to 50% weight by weight cresol in water. So next we have is co-solvency. So this technique enhances the solubility of very poorly soluble drug in water by adding water miscible solvent in which drug is very soluble. So the solvents used in combination to increase the solubility to drug solute are known as co-solvents, and the mechanism of co-solvency is not well understood. So it has been said that this phenomena takes place as a result of independent solubility of the solute in each co-solvent. So for example, undissociated phenobarbital has a solubility of approximately 1.2 gram per liter in water and 13 gram per liter in ethyl alcohol. And various co-solvents are commonly used such as ethanol, sorbitol, glycerin, propylene glycol, and polyethylene glycols. And aromatic waters are usually prepared by using this technique in which ethanol has been used as a co-solvent. Cinnamon water, dill water, and camphor water. And also in case of pH modification, pH is helpful in enhancing the solubility because many drugs behave as either weak acid or weak bases. For example, solubility of phenobarbital varies at different pH values. So pH is a critical instrument for the solubility of drugs, which can be found out by the application of the law of mass action to obtain a particular solubility of either weak acid or weak base drugs in the formulation. So the two equations to find out the required pH of Weak acid and weak bases are given below. So the pH environment for the adequate solubility must be compatible with the stability and the physiological conditions. So to maintain the pH for adequate solubility of drug information, suitable buffers are added, keeping Foley criteria in mind. So they must have adequate capacity in the desired pH range, and they must be physiological compatible and safe, and they must not affect the stability of drugs and other additives, and they must not affect the aesthetic properties of the formulation like color, taste, etc. So when it's come to the complexation, so many organic compounds in solution, they tend to associate with each other to some extent. So this association might have taken place by donor acceptor mechanism or Lewis acid base reaction between two or more chemical constituents. So it is too weak to be detected by standard techniques but can be confirmed by solubility analysis technique. So every substance has a specific reproducible equilibrium solubility in a particular solvent at a given temperature, and any change in this equilibrium denotes the formation of new species in the solution. So in case of weak acid and bases, the total solubility is equal to the inherent solubility of the undissociated compounds plus the concentration of the dissociated species. So similarly, when complexes are formed, the total solubility is equal to the inherent solubility of the uncomplexed drug plus the concentration of the drug complex in solution. So this increase in solubility of drug in solution can be confirmed by analytical techniques after finding out the total drug concentration before and after adding complexing agents. Typical example has been shown in the following diagrams, having the molar concentration of complexing agents and molar concentration of drug. So the graph having figure 5.3, it represents the increase in solubility of drug from points S to A due to formation of complexes, and at point A the solution is saturated with respect to both of drug and the complex, and the composition of solution is invariant from point A to B because as the drug in solution interacts with complexing agent, it is repelled from the excess present in the system and the additional complex formed precipitates. So since the solution is already saturated with respect to this component, so at point B all the excess drug has been consumed and further addition of complexing agent results in the decreasing the solubility of uncomplexed drug in solution. So if no further higher complexes are formed, the curve will come down to the value equal to the solubility of the complexes Rs. So it further increase in the curve indicates the formation of one or more secondary complexes. So it is a good technique for the enhancement of solubility of poorly soluble drugs. But again, a formulator must be careful about the following aspects. So, how does the resultant complex affect the stability and safety of the formulation? So, there must be compatibility of complexic agent in this regard, and also there should not be any untoward therapeutic effect of the complexic agent. And some examples of these techniques are as below. Solubility of iodine in water increased by the formation of polyiodides after adding potassium iodide, and solubility of caffeine is 1 ratio 50 in water, which is increased to 1 ratio 1.2 if sodium benzoate is added to it. So next we have is hypertrophy. So when the solubility of drug is enhanced owing to the presence of large amount of additives, the technique is referred to the hydrotrophy, and mechanism of this technique is not known, but it has been speculated that this change in the solubility of drug in solution might be due to either solubilization, complexation, or change in the solvent character. So it is a very good example of this technique is the enhancement of caffeine solubility in water due to presence of large concentration of sodium benzoate. So next we have is chemical modification. So this is the ultimate technique to enhance the solubility of many poorly soluble drugs by modifying them into the water soluble derivatives. So it has been found very much useful in enhancing the solubility of beta-methazone alcohol in water, which is 5.8 mg per 100 ml at 25 degrees centigrade, but the solubility of its 21 disodium phosphate ester is greater than 10 gram per 100 ml at 25 degrees centigrade. So nearly about 1500 times increase in solubility. So other example is the enhancement of solubility of alkaloids in water if converted to their salts. So no doubt it is quite useful technique, but the new compound must be undergone all the tests as in the case of parent compound like biological activity, acute and chronic toxicity, pharmaceutical evaluation and clinical testing. So students, this is all for the day. In the next lecture we will start from the preservation and viscosity. So thank you so much.